Hi, my name is Thanh. I'm a master student at Korea Research Institute of Chemical Technology. Today, I would like to present my thesis, which is on bio-based nanocomposite with upgraded mechanical strength and composability. This presentation consists of 4 sections. In the first section, I will go through the current plastic situation, and the section 2 will introduce the synthesis method for furan-based polyester. The section 3 provides us with the synthesis of PBAF and PBAT composites, results as well as discussion, and the final section is the conclusion. As you may know, plastics is an indispensable part in our life. Plastics have grown exposed naturally due to their outstanding property like lightweight, high flexibility, easy processing, and low cost. It is estimated that up to now there have been 8,300 million metric tons of primary plastics have produced, and this amount are projected to quadruple by 2050. However, the current plastics economy is highly linear. They are produced, used, and discarded at the end of their life, leading to excessive lasting waste accumulation and in the environment. Recent data shows that only 9% of the discarded plastics in 1950 have been recycled, while the rest end up in landfill and the environment. As part of waste mismanagement and incineration plan, this heavily impacted our natural environment. Plastic decompose in landfill over a century, and the available space for their burial is becoming significantly limited. When incinerated, plastics release toxic substances into the atmosphere that can severely affect human health, and especially the current alarming microplastic issue that can enter the human food chain. As a feasible solution, the concept of circular plastic economy was launched in 2010 to replace the linear and process, aiming to reduce plastic waste and greenhouse gas generation. In circular economy, there are two main approaches: recycling and bioplastics. While recycling often has a drawback in terms of the limited cycling numbers, especially when the multi-material plastic packaging is widely used nowadays, thus rendering this approach ineffective and challenging in the long term. Um, Bioplastics emerge as a more promising solution because bioplastics refer to those made from renewable sources with or without biodegradability and comprise of a large family of material with different properties after as application. In general, bioplastics can be classified into 3 main categories. The first one is bio-based biodegradable polymers. They can synthesize from microorganisms like PHA here, or directly produced from biomass like starch or cellulose, or even chemically synthesized from biomass-derived chemical like BLA. The second category is of bioplastics is fossil-based biodegradable polymers such as PPET or PCl here. And the final one is also called drop-ins. They are bio-based, non-biodegradable polymers. They have completely similar properties to petrochemical counterparts, but they are made from biomass instead of fossil fuel, such as bio-PET or bio-PE. However, the current production of bioplastics still represents less than 1% of the plastic produced globally. Among the high-performance biodegradable plastic commodities, polybutylene adipate-co-furanoate, or PBAT for short, has shown strong film performance due to its flexibility and toughness. However, this polymer has 3 major drawbacks. First, PPAT is currently produced from the petroleum-derived monomers, which is terephthalic acid. So the advantage of biodegradability is offset by the lack of sustainable carbon neutrality. Second, PPAT is less mechanically strong than conventional non-biodegradable plastics, which impedes its marketability. And the third is terephthalic acid manufacturing process has been reported to heavily contaminate the environment. So these factors mentioned above have led to a high demand for environmentally friendly material with superior properties. In our previous study, we have synthesized polybutylene adipate-co-furanoate, which is PBAF. The polymer will exhibit a higher biodegradation in chemical and enzymatic conditions, as you can see here. And also it has a superior elastic performance and competitive mechanical property compared with those of PBAT. However, the tensile strength and T toughness of PPAF still need to be further improved in order to compete with commercial bio-based and biodegradable plastic film. Meanwhile, the conventional approaches of incorporating inorganic reinforcing agent into a polymer matrix through in situ polymerization has long been used to achieve sufficient mechanical performance. Despite their merits, the use of these inorganic nanoparticles are often discouraged due to potential health and environmental concerns. Moreover, insufficient mechanical improvements are often observed due to low inorganic and organic interface affinity. As one of the most abundant natural biopolymer, chitin is an excellent substitute for above-mentioned inorganic agent and can be used as a reinforcing agent for polymer. Chitin is highly stiff. Indeed, chitin is even stiffer than cellulose. Chitin also possesses favorable biological characteristics like non-toxicity, sustainability, and biodegradability. It can be extracted from biomass and can be functionalized for further application. Currently, furan-based polyester can be synthesized by several methods, including interfacial polymerization, solution polymerization, ring opening, enzymatic polymerization, and melt polymerization. However, the most widely used methods are polytransfer esterification and direct polyesterification due to high efficiency and high molecular weight. So in this study, we synthesize a chitin-based nanomaterials, which is called sulfated chitin nanowhisker as a reinforcing agent for PPAF and PPAT matches. The sulfated chitin nanowhisker were produced through sulfuric acid hydrolysis of both chitin, which produce highly crystalline nanomaterial by removing amorphous regions while simultaneously converting some primary hydroxy and acetamide group into sulfate ester and protonated amino groups respectively, as we can see in the figure 5.8. The sulfated chitin was then incorporated into the polymer matrix via in situ polymerization. SCH dot with high dispersibility was directly added in butanediol monomer, as can be shown in the Tyndall effect images here. The incisive polymerization involves two separate stages, which is trans-esterification and polycondensation. In this study, the samples are referred to as FFX and TSX, where F, T, and X represent the PBAF and PBT nanocomposites and the nanofiller contents respectively. So, in this slide, the characteristics of SCHW as an effective filler are shown here. The repair SCHW was 165 long and 22 nanometer in diameter, as we can see here in the figure 7. And also, while conventional chitin nanomaterials produced by hydrochloric acid mediated hydrolysis are well known to disper only in acidic media through protonation and of their amino group, which electrostatically stabilize the suspension. In contrast, SCHW suspension with sulfate half-ester content of 0.32, like we can see here, is stable in an alkaline environment due to the protonation of the sulfate half-ester group. We can see the stable dispersion of SCHW in different alkaline condition here. More evidence for the good dispersibility of CHW can be seen through its potential of minus 3142. This value is much higher than the cutoff value required for a stable dispersion. Moreover, the 5% weight loss temperature was determined to be 278 degrees. Those results suggest that PVF can be mechanically reinforced by incorporating SCHW because of good dispersibility. Because the good dispersibility of SCHW can be maintained in the final composites, which is also thermally stable during PBAF melt polycondensation, as well as its melt processing into films. After the synthesis of PBF and PBT composite, the characteristics in terms of the molecular weight can be seen here in the table number 3. The molecular weight of the nanocomposites are as competent as the commercial PBAT, which is 142 kg per mole. But we can say that the molecular weight of the neat PBAF is slightly lower than that of neat PBAT, 108 versus 148. This was reported properly due to the hinder asymmetric structure of the furan ring during trans-esterification. In order to support the sequence distribution of the copolyester is random. The randomness R value here is shown to be nearly equal to 1, which means that the distribution obeys Bernoullian statistics and all nanocomposites are random. So we further evaluate the interaction of SCHW and the polymer matrix through mechanical properties, thermal behavior, and the spin lattice relaxation time obtained from the solid state NMR. First, regarding the mechanical properties, the preparation method is known to profoundly influence the behavior of the resultant product. Accordingly, the nanofiller was incorporated into the polymer matrix through incisive polymerization and acid solution blending, after which FX0 and FX0.1 were hard pressed or solvent cast into film. Here the solvent cast sample are referred to as FX0, FX0.1S and FX0.1 respectively. In the figure number 9.8 shows that acetyl FX0.1S, which means the solvent cast sample, exhibits inferior mechanical property compared to acetyl FS0, which is here. This means that solution blending adversely affects the properties of the resulting nanocomposites. This clearly indicates that the in situ incorporation of SCH is successfully in terms of the mechanical reinforcement. Moreover, in situ TS 0.3, which is the PBET nanocomposite with 0.3 weight% of SCH, exhibit a lower reinforcement effect than in situ FS0.1. Furthermore, we can see it here, the in situ FS0.1 exhibit a 1.4-fold higher value for both ultimate tear strength and tear toughness. The superior effectiveness observed for FS0.1 is attributable to the higher polarity of the furan ring compared to the non-polar benzene ring, which facilitates better dispersion of the hydrophilic nanofiller. Also, the good filler dispersibility in butanedione effectively prevents the resultant nanomaterial from aggregating. This is further supported using 3D X-ray micro-CT. As we can see here in the figure number 10.8, where highly dense crystallized SCH appear white and the amorphous polymer matrix appear as black. As can be observed, the filler are evenly distributed throughout the PBAF matrix of 0.1 weight% loading. However, when we increase the filler up to 0.3, the hydrogen bonding between the nanofiller can impede the dispersibility of the filler, as we can see of a certain level of aggregation here. So in this case, the fillers seem to fail to mechanically reinforcing the nanomaterial in terms of the tensile strength, but just increase the elongation and break. In addition, the reinforcing effectiveness of the filler on PBF as well as other nanocomposite systems was evaluated. As shown in the SBI plot, incorporating of different types of filler into bio-based polymeric matrix generally result in tensile strengths of less than 65 megapascal and low reinforcing effectiveness value of less than 1.88. This indicates that inorganic nanofillers usually mechanically reinforce polymer matrix ineffectively due to weak filler matrix affinities. In contrast, SCH exhibits a reinforcing effectiveness of 5.6, which is much higher than those of inorganic nanofiller. Speaking of the thermal behavior of the PBF and PBT nanocomposite, we investigated this by DSC and TGA results. In the figure 12, the DSC thermoframe of PBET and PBF composites display to melting temperature, TM1 and TM2 here, that correspond to crystalline structure containing aliphatic unit like butylene adipate BA, and aromatic like butylene terephthalic or PBAT or butylene furanoate BF or PBAF respectively. The aromatic melting enthalpy delta M2 of PBAT is significantly higher than the aliphatic melting enthalpy at all nanofilar loading, which indicates that the crystallinity is dominated by the BT phase, as we can see in the figure 12C here. In contrast, in the PBF nanocomposites, the opposite trend was observed. The heat diffusion of the aromatic BF segment was slightly lower than that of the aliphatic segment here, which indicates that the BA and BF phase have relatively similar crystallizabilities. The difference in the multi-phase structure of the two types of nanocomposites is understood by considering the touch of war between the BF and BT unit against the BA units for crystallization dominance ring rearrangement. While the foreseen pi-pi stacking of benzene ring facilitate the formation of aromatic BT crystallized phases, the furan ring distortion impedes the crystallization of aromatic BF units. So, also by examining the changes in the heat of fusion, we can investigate the influence of SCI on the microstructure of the polymer matrix. As we can see here, when incorporating the nanofiller, the melting peaks of the aliphatic BA segment in both the PBF and BET composites and those of the aromatic BF in the PBF composite shifted to lower temperatures when the filler is included. They also generally exhibit a lower heat of fusion. In particular, the BA segment in PBF show a noticeably lower heat of fusion at 0.1 weight% than the BF segment in PBF or the BA segment in PBET, whereas the BT segment in PBET composite appear to be almost independent of the nanofiller loading. These results indicate that filler matrix interaction between the filler and highly mobile segments like the BA or highly polar segments BF, like the BF, are stronger than those involving the more rigid and non-polar BT segment due to favorable pi-pi stacking. Here we illustrated the microstructure changes in Fs 0.1 and Ts 0.3 based on the changes in heat of fusion. And furthermore, the TGA results show that the radiation of neat PBF and BBT occur at 356 and 332 degrees. This is mostly attributed to the aliphatic segment degradation. Then we incorporating the SCH at 0.1 at 1% increase the thermal stability of SS0 and TS0 up to 9 and 30 degrees, as we can see here and here. This indicates that the formation of more interfacial electrostatic interaction or networks between the filler and the polymer matrix, which hinders transition and prevents the formation of volatile compounds during degradation. The interaction of filler and the polymer matrix is further evaluated through the spin lattice relaxation time. So, it is known that the filler affects the microstructure of the polymer by changing their free volume and segmental motion. Such behavior can be assessed by measuring the spin lattice relaxation time. So, figure 15A to C compare the T1 value of different types of carbon atom in TS 0.3 and FS 0.1 with those of the corresponding freezing sample. As SCH incorporation induced noticeable changes in the T1 value of PBF compared with those of PBAT. As you can see here, at the carboning, the C alpha and C beta, and also the methylene group in the PBF was significantly changed after incorporating the filler, while in PBAT, these changes seem insignificant. In this regard, the SCH can function as an anchor that restrains the furan ring as the alpha carbon here, and inevitably enlarge the space around the furan ring at the beta carbons, and endow the neighboring moieties with greater flexibility or mobility. Those was illustrated in the figure 15D. Also, in the FDA spectroscopy showed the more intense at 15,082 and 15,074 peak, which correspond to CC double bond stretching of the FDCA unit in amorphous and crystallized region. Taken together, we can conclude that PBF loaded with 0.1% of SCH is more compatible at molecular level than PBAT. As a possible replacement for PBAT, we further conducted the biodegradation of PBF composite in combustion condition. As can be seen in the figure A, the freezing sample lost 53% after the 3-month period, while the composite lost over 91% over 3 months. And we can see further here the cavities and degradation in the composite by SM image. The higher degradation rate of the composite film is attributable to structural changes in the polymer matrix resulting from the presence of the filler. Furthermore, the fetal toxic risk are also conducted to evaluate its standards of a compostable material. The results indicate that a composite does not produce any toxic substances upon the degradation that contaminate soil and affect plant growth. So, in conclusion, an all bio-based PPF and SCH nanocomposite would repair. This material exhibits superior robustness during the lifetime and improved degradation after disposal. The material can not only reduce the immense pressure on petroleum resources, but also contribute to bridging the lab to market gap associated with furan-based polyester.